can you help me, please?
Are you okay?
Yes, madam. I'm still at 15 Isham Way. I need to find a way to, 1 second, madam. I
Sorry,
need
can
to,
you say that again
yes,
for
I
me,
need to
please?
find a way to Japan. Basically, Japan are calling me. They say they have to get there myself, for the housing, because social care department, I get people get houses when they're 18 years old. And I just want to get a house when they're 19 years old, but the council don't want to give me a house. How do I do that with the council system?
Right, the housing won't be open. You need to ring back
Yeah,
tomorrow.
madam, I don't know, but they are meant to do a long time ago. I don't know what happened. Basically, they said I should get them myself, and I told them I can't because my PhD is not working in Cambridge. And I said my PhD is not in Cambridge, so I'm gonna do it in Japan because Cambridge is not doing anything. Because Cambridge can pay for it, but they don't want to.
Right, okay. You're going to have to phone them back tomorrow on this number
Oh wait,
because we
uh,
can't.
madam, I don't know, but I don't think basically Japan is free housing. When you turn as 15, but it's free for me. I don't think they'll give me though.
Japan.
Yeah, for a PhD because Japan has health and social care system too. Free housing. Yeah, I
So
know.
what is it you're phoning for?
Yes, house, but the one in Japan is free, but the council can pay for it basically. I don't know how they can support me with that.
Right.
Yeah.
If it's a free house, why do the council need to pay for it for you?
Yeah, because under Health and Social Care Act 2014, and they didn't want to give me a free house because I'm still in Thorac, under Thorac. I'm 24. I'm not 25 yet. Care leavers
Right, they,
program.
they
Yeah.
can't just give you. They can't
Yes,
just give you a free house. So you
madam,
have to.
I'm homeless in a care home. I didn't bring myself in a care home, madam. The council put me under it, but I don't have any contract under the care home. So basically, they said to me, they have to try again for myself because I don't know why they do that though.
Right, okay. You're going to have to call back tomorrow because we can't deal with that today. You have
Okay,
to call back
madam.
on this
Okay,
number.
madam. Basically, I told them yesterday that I called the boss, and the boss should help me sort it out, because it's a free house, and I don't know, because they say this is free, for me, but for me, that's why I came social care, but they told me no, so I don't know how the boss is gonna deal with them. Hello.
Okay, yeah, you're going to have to call back tomorrow because we can't deal with it tonight.
Madam, is there any way, shape, or form, like any pathway I can take, any way, any shape I can take a master's grade and get free house to the council act, because they love to lie on my name. Hmm? Hmm? I don't know, madam. Hello, madam. Madam.
Hello?
Hello. Basically, I don't know how to get a lie. But, basically, I told them that it's my right under the law. I've tried young council, I tried Dagenham council, I tried other councillor, I tried money, I tried bribing people, I tried everything I can. So, if I don't go to Japan right now, with my for after the lawsuit of 420 million pounds, they won't give it, but they give it in Japan because Japanese system better. Japanese can do it better. Can sort the money program out. Because they said she's a counselor, I have to do it online. So I can do it online in Japan. I don't know why, madam. But that's what they say to me because I don't have to go to court because I'm so easygoing or hardgoing, I don't know. Because they said if I come to court, they can be there, so I lie for them. So there's no point in anybody go to court. Just do it on moneyclaim.org for their bank account.
Okay then.
Madam, that's not fair though. They don't want to give me a house. They want their bank account. I don't think it's fair because they lose money. Madam, can you tell me how this how I can get my issue sorted out with housing?
No, you're going to have to. Is there anything else I can help you with?
Yes, how wait,
No,
yes,
you need to call back tomorrow.
madam. If you can't help me with housing, how can you help me solve my issue then? If you can't help me with the housing, hmm? You can't. I don't know. Not a lot of people can help nowadays. I'm so bored of it. I'm like thinking of like leaving to Japan forever.
Okay.
Yeah. Japan is much better there.
Okay, yeah,
Yeah.
if that's what you think, then yeah,
Yeah,
go to Japan.
madam, I'm doing my PhD there, so I have to go because Cambridge is not doing anything. I called Cambridge. They said the council will give me a house there. They can't help me get a education. It has to be in Cambridge. for the occasion, but they meant to give me free house, so they don't want to do that too. I don't know. And I called Mensa. I said Mensa is so small. The 2% out. They meant to give me all the support I need. But they won't give me my information, my data, my GD. I don't know why, madam. I was talking about this so much. I tried to give you my information. They don't want to do it. So say I don't even care about Mensa Japan. Because you don't respect me, madam. I tried to get my data. They even help me find my credentials, my passport. Basically, I went to mensa.com, BritishMensa.com, which is mensa.org, the UK, org the UK, and I went there and I forgot my password and don't want to give me a password. And I have a data recovery service now. A long time ago I had this, but I tried to use it, but they want to do for me. I don't know why, madam. Because if I log in, I can go to Oxford, I can go to Cambridge, I can go to Japan, I can go to America, and it'd be free of charge because my mom didn't want to help me, my dad didn't want to help me, because that's my right to independent. So basically, I don't care about Japanese Mensa or Nigerian Mensa or Tokyo because if I have to pay, it's a problem. But if you're part of Mensa, it's all free. That's the right. That's how your dedication works when you're really small, apparently. But all my friends have moved on in 1018. I'm 25 or 4, and I miss my friends in Mensa, but I can't find them anywhere. Madam, I don't know how I'm gonna find my friends. I have to start scraping the internet for their names. It's kind of a hard night for me because I have to work on the program, Python file to draw. I have to write a Python code for them to find their names. Because when they come out to the news, I have to find how they are. So I have to search them up on the internet to see what their names are. I already know their names. You know what I'm saying? On the internet with Google APIs.
Sorry, I've got another call coming through. I'm going to have to terminate the call.
Okay, madam. Have a lovely night.
Okay, bye-bye.
Bye-bye. Just lose people. Anyway, so basically, this is what I was gonna make work on anyway. This is gonna work on. But I can do it 2 minutes. Let's just do it. So basically, basically today's video, like I planned it. Basically, I'm trying to model some kind of ISO state machine, isotope, a canonical isotope state machine. For this, but isotope just means the bare minimum you need. Bare topology. You have like the neutrons, which are the all the you get a proton. A proton has you have a proton, which is like a positron. The proton is positively charged. You get a neutron. The neutron is what? A neutral, and electron is negative charge. So if you want to excite an electron, you give it positive charge. If you want to excite a proton, you give it a negative charge. Because that's basically if the negative charge is stable isotope. So basically, isotope definition. The isotope of a proton is positive, because we are a proton, and neutron is a neutral ground, and the electron. Obviously, you have the canonical mass. The mass of an isotope is mass. If the mass is the weight or the space it needs, this and the time. The mass canonical is canonical isotope between space and time. So if the mass is space, or if is space, you need dimension of space. So you have example. If an electron in the third dimension, e to the power of 3 has e to the power of negative 3. Plus, you get plus, minus, minus. If an electron to the power of negative 3 has a positive e to negative 3 means e has to get a charge of positive 3. Because the electron of negative 2 has to get a current to be excited, to be isotope, and this will give some density. So the density is defined by the isotope layer. For example, E negative to the power of 3 is the standard mass for isotope. Now the mass is the E3 times 3 negative 3 times negative 3. What we call the standard topology stable mass. E plus minus 3 equals minus 9. In the worst case, because mass is the size, or 9g. So this will be times the gravity, which is I don't know the gravity factor, but 9 minus 9g for this electron to be in a stable state. Now this proportion can be it can be get minus 3 plus 3 equals 6 minus 6. So minus 6 to minus 9 is the minimum, the maximum. So the maximum you need to excite is minus 6 times gravity, the canonical state of gravity. But if this is a chamber, If it's a chamber, you just need -6 because that's only the state of the entropy to entropy, based on the thermodynamic principles of entropy, from two effect. So -6 plus -9 is -15. Now -15 is all you need for shared state. So if you want to distribute it equally, minimum you need, or the maximum you need, the minimum and the maximum you need, share the minimum first you need to the maximum. So -15 is the total mass of shared state. -15. Now -15 would be -15 union, which is times and multiply, plus and multiply. This represents some kind of canonical state of shared problems. For example, with the lattice. What I mean by that is you get the lattice defined by the topology. Now, basically, lattice is just a field equation. So, the lattice basically got something called a field equation, but the field equation isn't parted. It's basically the field equation is the what used for the calculus. For example, liquid has a field equation, but that's only lattice only. But lattice is not good enough because there's tomography involved. So, lattice is very good for volume area to volume, plane or topology to volume. But if you're doing with electric field only, we're concerned about what electron. So we get a negative charged electron, standard negative charged electron, to the degree of -3. That's e to power -3, where the -3 is power. So if you get any set of electrons, e to the power represents e to -3 plus -3 equals -6. Now, -6 is equal to -3 plus -3 times -3 equals -9. And then in the total states, you get the minimum state of plus union, and then times. Basically, you have to times it when you get the maximum. So you get the minimum is 9. That's 9. The minimum to maximum, or the maximum to minimum, is -9. And you get the union, which is the add maximum to minimum, is -15. And then -9 to -9 times -9 is what? -9 to -9 is -81 squared. So 9 times 9 is -81. So that's -81. So you get -81, -81. Because this is two dimension. This is one dimension. A first dimension equals 1 of basically this is x dimension, should be x plane, one polar plane of x. Now the polar concept is this 81 is just not 81 squared. So basically for 3 electrons, for -3 charge, for the dimension of 3, 3 first, you need 81 squared space. But if you need 2 squared, 2 dimensions, very important. If you need 2 dimensions, 3 dimensions first, -3, you do 3 equals 81. But these 3 dimensions just means 3 charges again. The charge is like x, y, z, mapping to each dimension of the space. But the inverse wall is the cluster, the worst case for the 3 dimensions. So in the 3 dimensions, there are also 2 to the power of 2. So 2 to the power of 2 in this case is 9. 3 times 3 is 9. 9 times 3 is 9 times 3 is 27. Now 27 states or spaces, the configurations you can be in. So 9 times 3, you get the inverse. We get 2 to the power of 3. So that'll be 2 times 2 times 2 equals 4. Then 4 times 2 equals 8. Now this is 8 configuration, 8 pairs for every 27 configuration. Obviously for every 27 things you can model, you can only observe or act on 8. 8 bits of information. The idea I'm proposing for the something called the digital quantum system is basically radiography. Basically, the radiography basically you can use radiography to model this. But when you send a signal, you can basically distill it. So, for example, this is a real right train. This can be modeled as a real right train. Because when you distill something, you will have to use gradient tomography. For open motor, I call it. open motor, for noise coherence. Because if you start with noise, if you start something, you can get a signal of a stop, and that's the big problem here. I'm trying to give more from it. Now, the what do you mean by signal start as we're saying? For example, if I have a start symbol, if I say yes, 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 or yes, basically this is on or off in a sparse state. So we can have how many on-off states? That are 2 bits. So I can have 0. 0 can be in a state of iota, which is default off. But this 0 can mean 1 for on as well. So you get 2 states, 0 or 1. So you get the marks operation. So X, so you have a marks. The marks can be triggered noiselessly. If you have 0, 1, basically it's like it's like me trying to run on a treadmill machine to power it on. So you run the treadmill to power it on, or like a penicillin device. You then learns to from what you run. So you can have so if you're running on a treadmill to power it on, you can power it on by running. No, that's the idea. You don't have a start button there. You have some kind of input that is based on environment, but the environment has to measure you ontologically to see whether you are cheating. It's like me, it's like a lady. Oh, this is a good video I want to do now. So this is like a lady from so basically sparse line. I'll come out this video here, but this I'm saying. So you basically got this video here, Peloton device. So you just see this Peloton there. So you basically see this Peloton device. Basically you get tomography. Basically this is just basically I'm saying that basically you got this lady. Basically it's a bi-directional priority system based on learning heuristics. But basically that's what I call it. It's a sparse tomographic tomolization system. For example, seriously, this is like a this is what I'm saying. Basically, what's that Peloton? I love this myself. Basically, this is Peloton. I love Peloton. Oh, you see this? La 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 la. It's not perfect. So basically, it's a Peloton that is a woman line up. Okay, so basically, this one was riding a Peloton. Anyway, so you get say example that you are to power on. You are all learning. Well, basically, a node in the system is learning. So we are learning from each other. So I'm learning a present. Basically, I have a time, a space and a time, a consensual space time that we map together. Especially, we share a space, consensual space, and share time. But we are distant. We are equidistant. For example, I'm a teacher and I'm teaching you how to ride a Peloton device, like a bike. But this bike is a Peloton bike, so I know my exact time, date, and my frame of reason where I will share a constant state of so basically when I go to your device part time, I power my device on because I'm teaching. But the problem, you go to your power device, you power your device on, but just by just being there in the device space. So basically, you want to learn from me, I don't want to learn from you. So you have to go to your device, because I'm the teacher, I'm the teacher, so I don't have to be ready. You tell me when you're ready. So for you to power the device, you have to you have 2 states on and off. Basically, you have 2 states on and off. Basically, the 2 states are really the same thing as the kind of the 2 states are here. So basically, on and off. So we share 2 states on and off. So do you want to learn now? That's basically, I don't wait for you. I'm a state of superposition. So I'm learning. So I have an Excel. So basically, I'm in a state of 1, 0. First, 0 first, and 1 next, and you in the state of 1 first and 0 next. So that's the model. 1 first and 0, basically, 1 first and 0 next. So for this to work, we get sparse shared model, and that'll be a context switch. So the context switch is basically based on priority emulation. We can have a shared state of epsilon, but we are pseudo state of epsilon, like a fake state of basically. We don't know when we're gonna turn on. So we get epsilon 1 or 0. And the shear state is the epsilon. So this is an epsilon resolver. So your epsilon is my epsilon too. you basically get 0, 1, 0, 1, 0, 0. Basically, if I get epsilon first, basically for me to start, I have an epsilon or and a 0, because that's the model, and you get a 1 and a 0. You get a 1 and an epsilon. So that's the model you gotta preserve. But there's also a state of 0, 1. I mean 1, 0, 1, and 1 and 0. On the opposite pairs. Because that's how we connect on the protocol. So it's a bipartite system. So you get epsilon. So if I'm off 0 and 1, but 0 and 1 has two nodes. So if I'm in upslow state, I have a state. If I'm now at the 0 level, now 0 can be a 1 or 0, and this 1 and 0 is shared. So we share a 0 and then a 1 first, because and then you share and I share a 1 and 1 first, and then a 0, 1 and then a 0. Epsilon, and then you get 1 first, and then epsilon. 1 first, and then epsilon. So that's it. So you get on there. So you get that. So you get that's it. Basically, you get epsilon EE. So basically, we get a tree node of this. Oh, this is not good enough, man. I don't already know. So you get this 0, 1, 0. So you get epsilon 0, epsilon 1, 0, and then you get 0, 1. But it's giving too much protection. So basically, my nil is no your nil. Based on shared preference, shared preference. It shows that my minus minus has to be your minus minus, but your minus minus is your plus plus, and your plus plus is basically when you have two pairs of multiplies s cubed, they share an area of inverse area. So you have the inverse of times. If you do operation times, you are doing plus. You have doing add, two adds, and two multiplies. This if you do the multiply first, you are doing my add first, and if you're doing your multiply in your order, you have plus. If you do your plus times is my plus plus, and my plus plus is your times, because the inverse system resolves itself. So the kind of tomographic layer of this is just computing the x squared. So if you have 2 squared, or x squared, you get plus plus squared. But this is plus is a half of my dimension. So I have to transform it or rotate it into your dimension. So if for example, if I do a times, this is equal to half of half, which is 1 plus 1 unit. Plus this is just but if you do a minus times, you get minus half, minus half, and that's how you rotate the basically unit model. It's like a unit sequence. It's the fractional model of rotation, or the fractional operation, because there's some kind of lens in there. So I don't want to go into the depth of this, but the goal of this have this kind of radio system is for radio. Basically, when I have a channel, it helps like from read write. Basically, when I have to, when I have a R2, I can have 2 R. Because if I read something, if you read something, and I then read that information too over a radio channel, I get the polar equivalent. Basically, because language is fluid, signal is fluid. Basically, no matter the signal, the noise, if I get a digital waveform, and that digital waveform is analog too, I get 2R. Now 2R is the parameter, where the message is like in space and time. The message has a size. So basically, if I have 1,000 kilobytes, I also need 1,000 time. Basically, this will be why I need to make sure there's only noise in that system, because it's like system. The noise is basically 1,000 kilobytes over 1,000 message has to distill itself back into the system to have noise. So basically, there's no interception or relay effects, because you can't can't polarize information into itself because it's just noise when you try to do it. Because information is just part-text, can't be mixed of it in any shape or form. Because you know the way you do it, the first way you can do it is like see getting all the information space and then constructing the what's not the information and what is the information, which it could be. If the space is double, you know, basically if the space is 2 times the volume, then it's some pattern you can read. So if the space is 2 and the information is half, you know that there's a half is the information where the information lies, and that'll be all the information over this part of time. You know, so it's basically a half of space time. Basically share 1,000 kilobytes of space, which is 1,000 of the sound, 1,000 milliseconds, based on the UNO model. The other problem is the way is the part. So basically, you can have the way of the messages, and that'll be like the partite resolution. For example, if you have two reads here is one write. So 2 reads. So for example, you get read 2 reads, 2 people 2 reads, peer to peer. If you read it, I can read it. If I read it, you can read it. But you get this model. If you want to read, if you read it and then write it, I can write it and then read it. Information back. I can reply to it. But you know, because it's 2 writes here, 2 read information reads. All right, I can take this read and get it to it. Because if you get someone Eve, so Eve can literally rewrite it and write it here. So basically, if you have one write. So basically, this iota state of right. If I did the right and you know you did the other right here, we can reconstruct a read. You know the read because you know this right it can be it's not an iota state, and that's the main problem here. So the 2 rights are basically this problem here. So you have 2 rights read. You can have you can be real. Well, when you allow one read, one write. If you have 2 rights, you have 2 reads. If you have 2 writes, you have 2 reads, you know. So 2 writes, 2 reads. So the problem is this one is just one extra. If you have 2 writes, so if you write first, I can read it. But, you know, so Alice has the other node. It's an echo node, and Bob is an echo node, and Eve is always listening. So Eve can deconstruct any information if it's not half of the half a message packet, based on the training topology. So what I'm really going with this is what I call if you guys watch this video, be very fine. What is this? It's what I call the spring coil. The coil system is basically IK bound. So for example, inverse kinematic. So if you have half inverse kinematics, half messages, half the message. If you send half the message, you get 2 replies. You know, double the reply, padded. So you get half. So basically, if you get half a message, you never get one full packet. Send back. You get half. Basically, you get 2. You get double the basically, you get the padded message, the padded with noise. So the noise will be entropy from the radio signal, other radio systems, like you know, things that are radio bound. So if you send relay, you get you paddle with radio noise before you send them. So it's pre-fine sending. For example, if I send a full message, you get the full message split into halves, and that half will be the full message. But you have to distill it. So half message is half true, half false, and then you get the other half. So that's right, root, left, and then you get then you go back to the root and you get half. So you get half. So you get half true. Then if you swallow it half again, you get a quarter. So you get 2 quarters here, 2 quarters, half. To get a quarter, which is 0.25. Now, the 1 quarter here, so you get 1 quarter true, a quarter of true false, 1 of false is what? So you want to distill the false, and the false will be the fake. So if you get a quarter information, this will be enough to scale it up. So you want a quarter to 2, which will be times 4. Minimum, local minimum, based on radiography techniques. So you can see all of those, but they see nothing of you, because you know if you do half times 2, you just get a quarter, and that quarter is like 2 hops, 1 full hop in 2, 1 full hop in 4, and this thing can never be mirror the analog coherence so for example, so you get the model here. So if I read, if I read, I have my read. So I have my read. If I read, I'm what writing. I am writing. I am writing. Basically, if I'm read, I'm executing and I'm writing. If I'm reading, sorry, I'm executing and writing implicitly. So I have the state of right. So I'm doing half a right, half a right, and what half a right, another half a right, because I'm sending so to something, and these two half right, so you get two half right, and then if I then go to the execute, so if I then go to the right, if I'm doing writing, I'm doing half an execution, I'm executing some code, and then if I'm doing half an execution, read the execution, and that's be my send. Usually in real time, I'm sending something. So in the system, I'm sending something on the two balance, half read, half write, half execute. Obviously, I'm doing half of everything. Half read, half write, half execute. But I want this to be a quarter of everything. So the quarter will be, sorry guys, distilling everything into its essence, essence, so we can have half of a quarter of everything, all noise, and all message and no noise for us, ecological. So you have this. I'm trying to make it form the I'm getting. So whether the electric wire, electric magnetic field, the coil is like half the spring. So the spring, so look at the spring. The spring is the medium or channel. So if I pull the spring down, I could give it potential energy. Now that potential energy kicks up 2k. To say you get half k. So if I pull half the spring, try to listen to it like some kind of trying to get like a coil that and listen to it this way. I get half the spring and then put my ears there. I listen to it. I'm listening for information on the end, but this is the pipe I am not meant to put. It's not my pipe, so I can do that from some kind of basically I put my own coil, and try to listen to it. I'm Eve, so I can listen to it that way, because the coil is always there, but coils are always available. But I can then interpret it. That's what's very important. I can interpret it with buttons and stuff. So I can interpret all the stuff and get the full information. That's the main problem here. Basically get bus topology, ring topology. If you go to a tutorial point, you can see all of this empty. So you get peer to peer. This is peer to peer. So we can see all the information, but it takes time. But we have to ensure there's a cutoff point in time as well. So we can cut off in space and time. So the message becomes noisy, internationally noisy, because the space equals the time at the local maximum between how we interact in the channel, and that's what I'm saying. You get peer to peer, supposedly back and forth, up and down, based on DAG. So if you get AMX, if I read the worst case mag, for example, if I send 1,000 kilobytes and 1,000 over 1,000 seconds, I get a O1 construction, auxiliary construction. But that has to be the inverse to of the negative 1,000 kilobytes and negative 1,000 bytes. Based on the information delay protocol to be coherent. Because if you get get plus, you get minus, and that's what you get. You get when you get 1,000, you go lose 1,000 kilobytes. Basically that's the sparsity model. So when you get 1,000 bytes, you get O1 protocol that's positive, but you want to get O1 protocol that's negative on the electron space. So basically you're gonna do nothing for that set time with that space information space. Basically you can't use that device ever. You can never switch channels for no communication. You have to do it automatically. And whatever image you have to do is distilled onto your TV, my TV. I'm gonna be my TV. I'm watching the image in real time, but the information is real time vision because it sees with the antennas. It doesn't. What in you get a radio dish. It sees with the radio dish, and the radio dish is what relays to you what's happening in real time. Because if you get one you can see and one you can't see. The one that's more important to see is really see what's happening in all angles, based on the pi model, the bubble cordial model of pi. So I see what's happening in real time because the pi releases everything. Because this pre-5 synchronous. And I'm saying, if I then split a quarter of this to what I see in that time, what I observe of the radio is, I split other quarter to what I cannot see, on my noise in that time, and that'll be my half of security, and the other half will be in parallel to the space. So this is time bound. the space. I get the other half from the space around me, and that'll be the quarter model, and that'll be my real-time relay to my screen, to distilled into my radiographic screen. You know, like when money is all the video on the glasses. You know, and you get 10,000 for the second. So basically, I don't even want to touch the time. I don't want to touch the time. The concession time, because it's just me in that frame of mind. But if there's a meeting, we use a peer-to-peer model, and we be there at the same. The best case would be in the same room, you know, because we don't have to be in the same area. But you know, in the worst case, we'll be across in different compound complexes based on our relay hubs. Basically, the channel never disconnect because we configure the relay system on the fly. You know, because you can recompute the steps. Because if you see, it's like me taking a radio from one place to another. You know, it's no based on quantity. If I take a radio channel, you know, get a change channel to anywhere around the channel I am with same configuration. I just copy the same state, my code state, and never change the channel or whatever the system was the state at that time. Then I have really just I'm the same person. So basically, this means I'm the same person. Unless I give it to someone else, then I fucked up. But it's another problem for another day. So the idea of this radio is to see everything and nothing at the same time. So when enemy see nothing, anyone will see nothing based on the natural entropy of the world. Entropy of the world, which would be like we taking the radio wave, causing problems for someone else, someone control for me, or vice versa. And the idea is to have the coil. Basically, when you load the coil, you are pulling down a spring, a pinpoint spring, and basically you're not launching this coil. You're not letting go of the coil. You are basically you're not pressing a button to basically like you're pressing like any button to pull the coil. But the pulling is like a digital signal to get the digital. If I hold something, that's the delay. So by holding it to execute it, so I have something of delay. So the delay is buffered, and the buffer is like the hack thing. So basically, when you get a stack overflow, you have a buffer that is in if the buffer is reserved, you can't use it. Someone else is using it. It's like inverse lock, because it's locked for you because you can access the memory or time. But because I'm holding the spring, and the spring has to be I'm holding the spring, but the spring is mine. So for you, you'll see the spring as used. But how can people do this? You're supposed to stack overflow or buffer overflow, because in digital form, because you are that much ready for you to use. But for me, it's kinetic energy. Basically, for me, it's potential energy. I can be in that state of one on. Basically, if the execute state is on, one execute equals one. Then I'm in that stage read write for read write execute. But that's my user state. But you are but I can be on the inside. But for you to be off, basically for you to use that state, turn off my off after switch to a different channel. Because that's how you switch all the contexts. You don't give anything out because this context switch. If it's not being used. If it's not being used, there's some kind of noise buffer there that reserves the memory or the channel. So there's no quantum switch based on electrical pulse, electromagnetic systems for the protocol. So you only see what you're meant to see, what you're allowed to see. Not what you're meant to see, but what you're allowed to see. What you're meant to see, what you're meant to be doing or seeing, but what you're meant to be doing. So basically it's all noise when you head through when you hop channels that you're not actually using based on the Radiomogpry model. Thank you guys for watching the video.